Hello, my name is Blair McDonald. I'd like to share with you some discoveries I've made about the atmosphere, or that have come about through the climate debate. I was investigating these special greenhouse gases and interested in the non-greenhouse gases and exactly why are they non-greenhouse gases when we are surrounded by radiation, infrared radiation. Why are they non-greenhouse gases? And this has led me to discover, in summary, that the whole atmosphere is a greenhouse gas. It's just that we are not pulling all the science together. We have some amazing technology and we have some amazing knowledge over the last 100 or so years. And there's been a lot of misinterpretations, and this is what I've found, and I want to show you what I've done. I've written a paper. It's at academia.edu. I don't expect anyone to publish it. You know, I know that it's a real it's a bitch fight out there at the moment in this area, and I'm not wanting to get involved in that. I just like good science. So where I've started off from is I was drawn into the Tyndall Experiment, and I looked into this experiment. From there, I went on to look at Raman Spectroscopy, and which is the parallel or the complement to the to infrared spectroscopy, and then I've augmented the two together. I have a full atmosphere now, and I feel comfortable that there is no special greenhouse gases. The whole atmosphere is a greenhouse, if that's what you want to call it, gas, and majority of them are nitrogen and oxygen. This will come as a surprise to many people, and I've got to prove it to you, I guess. So if you let me, I'll do my best. Okay. So I'm going to go back now and look at the Tyndall Experiment. So here we have the 1859 Tyndall Experiment. This is what derives these special greenhouse gases, and what is special here? Well, just before the Tyndall Experiment, there was a breakthrough in physics. It was thermoelectrics. It's not talked about a lot. You can't find it in textbooks. You have to drag it out, and when you do, you can see that there's a whole area: thermoelectrics and the Seebeck effect. Now, the Seebeck effect. What's Seebeck? Well, without getting into the physics too much. You can do this, but it's basically the temperature gauges that you have in your car or wherever. He developed the thermocouple, and soon after, they learned that if you put many thermocouples together, you get a thermopile. And this is what Tyndall was using. This is his thermopile here, and the thermopile is wired up to a galvanometer. This is measuring electric current. Now the electricity is very small amounts, and this is what we've forgotten. I think this is where we got off track, because this is exactly what he's produced, what he's measuring is electricity. What else we can see in this is that he's got a heat source. That's important. Two heat sources actually. So he's got a control, and he's got a there's his control. Yeah. And he's got another one over here where he isolates the gases in here. So we can, now in the time that, since this experiment, that's a long time ago, well, thermopiles are ubiquitous today, and they are found in technology like this. This is a $30 US non-contact infrared thermometer, and it can measure temperatures 31 degrees from my hand. Now let my hand be the heat source, if you like. And so what's interesting is that it measures my hand, but it's not measuring something else. It's not measuring the air in between my hand and the detector, the thermopile. You can source whether it's a thermopile. You can do that. It is a thermopile, and there'll be a little galvanometer, and it will be calibrated to the temperature. And now it's not perfect. If you look at where this technology is used, you can see that there's problems. It's not perfect. It doesn't pick up a perfect black body, but it's pretty close. But it doesn't measure nitrogen, and it doesn't measure oxygen. And he didn't measure nitrogen, and he didn't measure oxygen. But we know now why. We know a lot more. You know, quantum mechanics has has evolved through that time. Physics, technology, different technologies, and we know a lot more. So this, I'm going to show you something. Here's a glass. Now I'm going to measure the temperature of the glass. Hopefully you can see that, and I've got 21 degrees. Now, if I put my hand in the glass and do the same, it should measure my hand, but it's not going to. It's going to measure the glass. Now the reason, well, it's transparent to the eye, but it's said to be opaque or absorbing. But this is misleading. This device is generating electricity from the substances it can see. And in terms of the glass, the glass is a thermoelectric substance, and that would apply to anything that's thermoelectric. And it just so happens that most of the molecule of carbon dioxide or water are thermoelectric, and this would be the well, in the sense, this would be a thermoelectric, a greenhouse solid. Rather than a greenhouse gas, this would be a greenhouse solid. So that's a very strange thing to think. Now, there are solids that are non-thermoelectric, like nitrogen and oxygen gases. And what have I got here? I've got a book. So, I mean, this is called germanium. And if this was germanium in my hand, I can't afford germanium. It's very expensive. But it's used in all thermoimaging cameras as lenses. Interesting. And you can, it would measure, what would it measure? What would it measure? What would it measure my hand? It would see right through it. And I just went as a thought experiment. Imagine if the whole Earth was made of germanium. Then this instrument wouldn't measure it, but measure the temperature. Well, most of the atmosphere is made of gases that are non-thermoelectric, and well, this is quite useless, but it's fantastically useful if you want to measure the quantity of carbon dioxide. And so a CO2 sensor will use exactly the same apparatus, only in a smaller setting. And modern day technology uses with spectrographs. All you have to do now is split the whole frequency through the infrared range, and they do that. I'm going to show you a schematic. Here's a schematic of the of a spectrograph. There's the heat source, my hand, right? But this time it's split, just rather like a CO2 sensor. You have a sample, and you have a control, a reference, and here's a splitter. That splitter, it'll go right through the spectrum, the electromagnetic spectrum. Detector, that's the thermopile. Computer processor in here. This is what Tyndall didn't have, but well, he could take notes, couldn't he? And a display. Okay, this is what's come about in the time. So so we can look at it at a spectrograph, and this is the range of at wavelength and wave numbers through the infrared range, and these dips and troughs correspond to what is said to be absorption, right, and transparency, and this is on this axis here. Well, look, I'm going to overturn this just purely on the mechanics of the thermopile. What this is doing, and hopefully if I go down, is a thermoelectromotive force in voltage. This is the anomaly between the heat source and the gas in question. And so when you add the gases, it'll dip, and it'll well, I'm going to use the word absorb, but there'll be an anomaly. It'll measure the substance of the gas. Now you see, the thing is, the heat source are very hot in those machines. I've learned that they're some 1,000 degrees. I can't believe that myself, but they're very hot. So any other gas coming in the sample chamber will show up and block it out, because it is what it will measure. Okay, so that's what they're measuring. Here's what they call the infrared window, and this is what this is set to. It's quite a broad range, and it's set to that range, so it can pick up and can read most substances. Okay, without being affected by the atmosphere. Okay. So what I did now is I went on to look at the non-greenhouse gases. I feel comfortable that there's been a misinterpretation with the greenhouse gases. But what are these non-greenhouse gases? Well, they are non-thermoelectric substances. Now, what we need to look at is the area of science that deals with these. And the area of science is with the spectrographs, the infrared spectrographs, because they understand why nitrogen and oxygen don't show up. They have explanations for it, and it's all to do with the vibration of the molecule. Now let's have a look at what I've got here. Here's some images of the vibrations. Now, I'm no chemist, but what we're looking for here is, well, we've got an antisymmetric, a symmetric, and a scissoring. Now, the important one for us is the symmetric. Wherever you see symmetric, these molecules will not, these vibrational modes is what we call them, they will not show up with a thermopile. Okay, that is the crux. So if we go down, there's water. Okay, so that's fine. So water has a part that it's not showing up. That's interesting. Carbon dioxide, symmetric. So one part of them, so molecules have degrees of freedom. They have different vibrational modes. But nitrogen and oxygen only have one each. They only have one, and that one that they've got doesn't show up with this. So that's going to be the crux, and we're going to see that. But if you take carbon dioxide, well, it has 3 that do show up with this, and 1 that doesn't. And here's methane. It has around 6, I believe, and one of them shows up. 5 of them show up with this. So they are greenhouse gases, right? But one of them is symmetric and doesn't. So we need a test. We need a test to find where they are. Where are these vibrational modes? And there is. This is quantum mechanics. This is the Schrödinger equation. Now, I learned this. It's there. It's very easy to find. It's just a path towards this. And I found reference to the vibration frequencies of these molecules. Let's have a look. Here is a table coming from a source. I found several of them actually. It's a journal. It's published. And here's nitrogen, and here's oxygen, and there are the important. I've discovered that in the Schrödinger equation, there's the important numbers, and they correspond to the vibration wave number of those molecules of the symmetric vibration. And well, then now you need a test. You need an instrument, you need a technology that can identify it, just like this would. Well, there is. This is unbelievable. There is. It's called Raman Spectroscopy, and I don't know who's full. I've actually asked scientists who have you heard of Raman Spectroscopy, and some have, and if they do, they don't know much about it. Look, Raman Spectroscopy is the complement to this. Can you believe it? You've got a complement. It shows what this doesn't show. And so when I found that, that's exciting. So what you would expect is that you would expect to see that there's a vibration and it shows up in the Raman. Well, oh, it does. I've got several references to this. Here's one. I'm going to flick down here. So here's nitrogen, and it's right there in that predicted. If you go back, you can have a look. But you can have a look. And there's oxygen right there where it predicts it. There's only one, remember? There's only one, and there it is. It's right smack in the infrared range, right where it's invisible to this. That's why I'm so confident we have a full atmosphere now. And here's a schematic of carbon dioxide. There's your infrared, 2 of them at least. Yeah. And then there's the Raman, the complementary, and so you get the full set. Okay. So, and methane has a similar, right? You recall, methane has a similar setup. Here's another reference. So there's a Raman, and it's just showing up. There's the nitrogen and the oxygen, the wave numbers, and they are right in the infrared. So again, they are predicted by Schrödinger. They are, and they are observed by Raman spectroscopy. So on its own, here's a Raman spectrograph. It's a schematic, and all I did was I just put, there's no intensity here at all, it's just Raman active vibrational modes, boom, 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 boom. So we've got methane, nitrogen, oxygen, methane again, and carbon dioxide. Okay, so now I augmented the two together. This is the say thermoelectrics and Raman. Now thermoelectrics, I mean, they do have a fantastic application. They show the fingerprint of the atmosphere. That's what they show. And here we got the Raman to go with it as a complement. They work. Now we've got a full set. Okay. Now I've written to both. No, I haven't written to both. I've written to the skeptic side of the in the climate debate. I'm actually not interested in the climate debate. Well, it'd be a bit of a lie, but I'm not really. I'm actually interested. I've been fascinated by the pure science here. So, but they don't write back to me. So if you like to review my paper or look at what I've done, great. But as far as I'm concerned, anyone talking about a special group of greenhouse gases, well, yeah, I can quickly just say, well, go and get one of these, and we'll just run through it, and I'll show them the evidence. It's just not the way they're saying it is. There's something wrong, and you have to reinterpret everything that's been said about the climate. You can't have a special group of forcing gases when the rest of the atmosphere is a greenhouse also. Then it would be just like saying you're adding glass. More glass has become a greenhouse solid. But we know about thermodynamics, and it's just not the way it works. You're breaking down all the laws of thermodynamics. It would just go to equilibrium. It would just equalize itself out. So carbon dioxide's not special. It's been relegated. But what has been relegated are the nitrogen and the oxygen, and they fit. And we are surrounded by it, and I'm comfortable with it. We're blanketed by a wonderful atmosphere radiating in the infrared, and isn't that nice? So I hope I get some nice feedback from this, and thank you for listening.